Alright, so at the end of the last section, it mentions that there are games which are not strictly determined. In other words, there are games without a saddle value. And let's see what happens when there's no saddle value. So here's a 2x2 matrix game, and let's examine what happens when we have this game. Alright, so here's the duplicate of the game, and let's consider the, as I said, the max-min strategy. This here, for the row player, the minimum payoff for second row is 0, and the minimum payoff for the first row is 0. For the column player, so these two are the minimum, these are the row mins. All right, then the column maxima, which makes the worst case for the column player, column maxima are 2 in this column and 2 in this column. So the green are the two column maxima. All right. So let's think about what these guys are going to think when they strategize. The row player is going to say, well, no matter which row I play, my minimum payoff is 0. So from that point of view, it doesn't really matter which one I play. However, if I anticipate the column player, the column player is going to minimize his maximum, and his if you take these two column maximums, the minimum column maximum is here. So the column player is going to play column 2. So I'm going to play row 1. If I play row 1 and column player plays column 2, I'm going to get a 1, and he's going to get a 0. But then the column player thinks on his side. He says, well, look, the row player knows my payoffs, and he's going to want to play row 1. So I'm going to fool him, and I'll play column 1. And then he'll only get a payoff of 0 and not 1, so he won't do as well as he thought he would. Right? So, and then the row player said, well, maybe the column player is going to double cross me and play column 1, so I'll go back and play I won't play row 1, I'll play row 2, and then I'll get a 2. So you see that there's this kind of double, triple, quadruple cross thinking that can go on, and there's really not one value that they both agree on that's common to both of them. Now that's quite different from the case where you do have a saddle value. So for instance, suppose the game were like this. Okay, in this case, let's do the same thing and figure out the row and the row maximin and the column minimax. The row maximin in this row, this 0 is the minimum, and in this row, this 1 minus 1 is the minimum. So those are both the row mins. Okay, and then the column maxima that give the maximum penalty for the column player. And here, if you look at this column, the maximum penalty is 2. And you look in this one, the maximum penalty is 0. Okay, so this 0 is both. These are the column axes. This 0 is both a row min and a column max. Now let's try to see if that same reasoning that we did for the other game applies here. The row player says, well, I'd really like to get the 2, and I certainly don't want to get the minus 1. So in fact, no matter what the other person, what C plays, I make off better by playing row 2 than row 1, right? If C plays first column, I make off better with row 2 than row 1, and if C plays second column, I make off better with row 2 than row 1. Now what does the column player think? The column player says, well, no matter what the row player does, I make off better with column 2 than with column 1. If the row player plays row 1, then if I do column 2, I get minus 1, which is good for me. That's a loss for row player. It's a gain for me. On the other hand, if the row player plays row 2, well, I get a 0. It's better for me to play column 2 than column 1. In this case, I would lose a 2. Right? So here you have a case where it's really intelligent choice. They both have an intelligent choice that they have a strategy where they will do better no matter what the other person does. But if this minus becomes a plus, that's not the case anymore. They'll kind of go round and round and try to outthink and outguess each other, and there's no clear answer. Now it turns out that there is a clear answer, but it's not a simple strategy. It's something called a mixed strategy. Both R and C will end up doing mixed strategies in a game like this, and we'll see that shortly. All right. So let's go back to the text and go to the next section. Okay, so let's look at 2x2 matrix games and see the conditions under which you do have a saddle value. If you have a saddle value, then the game is strictly determined. Otherwise, it's not strictly determined. So here we have a theorem for 2x2 games. The matrix game ABCD, these are unknowns. This game is non-strictly determined if and only if one of the following two conditions is satisfied. A is less than B, A is less than C, and D is less than B, D is less than C. In other words, this A is smaller than both of these, and this D is smaller than both of these. Okay. On the other hand, condition 2 is A is greater than B, A greater than C, D greater than B, and D greater than C. In this case, A is greater than these two, and D is greater than these two. All right. So in either one of those cases, you do not have a saddle value. And even more than that, if these conditions are not satisfied, then you do have a saddle value. So that's what the if and only if says. If I want to see if a game has a saddle value, all I have to do is check that neither one of these two conditions holds. And in that case, the game will have a saddle value. All right. So let's look at the proof and see how this works. All right. So this is a proof of if and only if. So there are really two things to prove. You want to prove that if these conditions hold, then there's no saddle value. On the other hand, you want to show that if these conditions do not hold, then there is a saddle value. So the two paragraphs in this proof correspond to those two conditions. This part is the if part of the proof. Okay. All right, so here he says, if either condition 1 or 2 holds, it's easy to check that no entry of the matrix is simultaneously the minimum of the row and the maximum of the column. All right, so he says easy to check. Let's see if that's true. All right, if this condition holds, first of all, if A is greater than B and A is greater than C, then A is not, let's see, A is the minimum of the row, but not the maximum of the column, because A is less than C. Here it says A is the minimum of the row, but it's not the maximum of the column. On the other hand, let's look at C. C is the maximum of the column, but it's not the minimum of the row. All right. Let's look at B. Under this condition, B is not the minimum of the row because it's bigger than A. So that's certainly not a saddle value. And in this case, this D is not the maximum of the column. So you can see that in this case, none of these can be saddle value because they all they all fail one or the other of the conditions. Same thing here. If A is greater than B, then A is not the minimum of the row, so it's disqualified as a saddle value. Also, we have D is greater than C, so D is disqualified as a saddle value. On the other hand, B is not the biggest in the column, so B is not a saddle value. And C is not the biggest in the column, so C is not a saddle value. So you can check the 4 values one by one and say, nope, none of them can be saddle values because these conditions make all of those things fail. Now, as I mentioned, you have to prove 2 things. You have to prove if and only if. We showed that if either of these 2 conditions holds, then the game is non-strictly determined. On the other hand, we have to show that if the game is non-strictly determined, then one of these 2 must hold. So to show this, I copied over to the OneNote page. Here's our game. So we're going to say suppose that G is non-strictly determined. Okay, and we want to show that that means that one of those two conditions hold. Now, in this case, then, either, well, if we look at just A and B, there are three cases. We could have A greater than B, we could have A less than B, and then the third case we could have is A equal to B. Okay, so let's look in case 1. Case 1, A is greater than B. Okay, and remember that G is non-strictly determined. And I'll just write that as NSD. All right, now, A is greater than B. That means that B is the minimum in this row. Now, in order for B to avoid being the maximum in this row, then it must be true that B is less than D, since G is NSD. NSD, sorry. Okay, like I said, if B were greater than D, then B would be the maximum in this column, so B would be a saddle value. All right, so we've established this, B is less than D. All right, now that looks like D is now the maximum value in this column. So in order to avoid D being the minimum in this row, it must be that C should be less than D. Okay? So we also must have because otherwise D would be the saddle value. All right, finally, we want to make sure that C is not a saddle value because C is the minimum in this row. It cannot be the maximum in this column. So we must also have, C cannot be the maximum, so C must be less than A. So what do we have all together? We have A is greater than B, A is greater than C, D is greater than B, D is greater than C. Go back here. This case 1 here corresponds to, actually it corresponds to case 2 here. So that's a little confusing. Let me go back here and renumber these. I'll call this case 2, I'll call this case 1, I'll call this case 3. So if I look at case 2, so this implies case 2 in the theorem. All right. Now you can go through the same argument. I'm not going to do it, but you can go through the same argument and say that if A is less than B, then case 1 in the theorem must also hold. Well, let's just think about it quickly. If A is less than B, then A would be the minimum in this first row. So in order for it to avoid being the maximum in this column, you'd have to have A is less than C. On the other hand, then C would be the maximum in this column. So in order to avoiding it being the minimum in this row, you'd have to have C is greater than D. And similarly, you'd have to get B is greater than D, and you'd get the 4 conditions of case 1. Now case 3 is disqualified because, as it says here, in the chapter, that exercise 8 of the previous section, if you have 2 entries in the same row have the same value, then the game is strictly determined. So that's an exercise that you can work on and do from the previous chapter. Okay, I'm going to split this chapter's video in half, so we'll stop here.